All right, well, happy Tuesday again. We're moving on to new stuff again. Linked lists are actually super cool, and this will be, it's a bit of a weird way of thinking about how to store data. So this will be kind of fun here to get into this. Again, I'm not super fond of how the textbook goes through and like everything is a subclass of another thing, which is good, it's great. Like you don't want to have to reinvent the wheel and do a bunch of other stuff. But it makes it harder to kind of understand what's happening behind the scenes. So when we go and write our own linked list, we're just going to do it all from scratch and not have to deal with any of that other stuff here. So this will be our linked lists. And the idea with a linked list is one of the downsides of our Python lists is anytime you want to modify a value that's not at the end. How slow is it? Right, in terms of like how many n items we have, if you say that the big O notation, like our average speed for doing something that's not at the end of the list. Because it was super fast to add to the end of the list. And we could say the amortized average of that is constant, because eventually we'll double, but really, the cost of that gets averaged out over all the other ones. So it's fast to add at the end. If you want to add at the beginning of the list or the middle of the list, it's all going to be O of n. The more items we have, the more stuff has to happen, right, as items shift down in the lists. So in order to add or remove items from an array-based list, it's very slow. So the linked list gives us an option where we'll see we can do that much faster. Now, what's fun with linked lists is we don't need to have one big block of memory like an array-based list does to store everything. And that's how we can do really fast inserts, because we don't need to shift anything around. We're going to add new items here. And I kind of think of these sort of like when you do Secret Santa. Like everybody knows who they're buying a gift for, but imagine that we made sure it was like a circle. So like, I bought a gift for you, you bought a gift for him, he bought a gift for him, to make sure that everyone was buying for the next person. So I don't know who the last person in the list is, right? I only know who the next person is that I'm buying a gift for. And they only know who they're buying a gift for, and they only know who they're buying a gift for. And that's what we're going to do. We're going to set up this sort of chain here, this linked list, where each item in the list is linked to the next one. So we're going to have a class for linked list here. And what linked list does is it internally uses a private class. So this is one of those implementation details, so the idea of abstraction. Anyone using a linked list doesn't need to know about this. Right? It's one of our private details here. So we're going to write an inner class, so a class inside of a class for node. So a node in a linked list here has some data that it holds. Right? It stores some data or some item or some element or whatever you want to call it here. This is the data that we're actually storing. And then it knows its next item in the list. And for now, we're going to default it to none and say, hey, you don't have a next. So we'll have self.data is the data. And self.next is the next. Okay, that's all node does for us. So it's just a way to hold these things together so we can have these pieces of information here. And then if I want to have an init method here for my linked list needs to know where the front of the linked list is. So I know how I can get to this first piece of information, and it needs to know where the last piece of information is. Because I need to be able to add more items onto the end of my linked list here if I wanted to kind of follow these things in order. So we're going to have a self dot. Now these we're going to mark as private, right? We don't want anyone messing with these here. So we're going to have our self dot front is none, and a self dot back is none. I don't know where the front is. I don't know where the back is. There's no items here, and maybe I'll count a number of items, right? A number of items. Track how many items I have in here. We'll start off at 0. And that's probably fine for now. So we can define a size or length, right, under length of self. We're going to return self.number of items. So we can figure out how long this collection is, how long this linked list is here. So now, if we make our linked list act like a list, you should be able to get at something from any particular index. Sure, you should be able to add something onto the end. So adding to the end or appending is probably the easiest way to start here. So we're going to define our append function here that takes an item, or maybe some data. I don't know what you should call it, data. Append some data. So we're going to take some piece of data and we're going to add it down to the list here. Now, we have some special cases here that these might be none. It's easier if they're not none, but we have to handle it. They might be none, right? We might have nothing in the list right now. So I can check and say, hey, if self.front is none, then my self.front will equal self.node given the data. Right? If I don't have a front item, right, my new front item is going to be this node, because node is going to know who comes after it. If I'm empty, right, there's nothing that comes after it, that's perfectly fine, and I can say self.back is self.front. Right? The back and the front are the same one, because there's no other nodes here in my linked list to follow after. Right? If it's, and then my later I'll add the self.number of items, self.number of items plus 1. So the other case that if I already have a front item, if I have something here, then what I want to do is I want to add this to the end of my list. So I can say self.back, because if I have a front, I must have a back. Right? They might be the same thing if I have one item, but if there's no items, they're both none. So if I have something here, my self.back, we're going to need to add something on to the end of that. So self.back, right, is a node, right? And node has this attribute of next. So we can say self.back.next then will equal a self.node given the data. Right? So add something on to the end. So I had, the number 5. There was nothing after it. So I'm going to add something that comes after the number 5. We'll add the number 10. Right? So now self.back needs to become self.back.next. So the last thing on my list now is no longer the number 5, now it's the number 10. So I'm going to change where my back is pointing. Right? Because my linked list needs to keep track of where the front thing is and where the back thing is. And this will work all the time. So if front is none, great. If I have a back, set something that comes after the back item or last item. I like front and back. You might call it first and last, however you want to call it here. Right? The item in the back. Does last make more sense in the back? We can call it anything. The front of the list, the back of the list. So then we just say, okay, well, what was the last item now? I just added something after that. So the new last item, new back of my list here, is that I'm going to rename that to last. I think that might make more sense. Let's go refactor rename. Let's say this is last. But it should go first then? Is that a front? We can say first. Refactor rename to first. Okay, so we have first and last. Hopefully that makes sense instead of front and back. Same idea here. So the last item is no longer the last item because there's something that comes after it. The next thing must be the new last item. So we get this really weird looking like this dot this dot this kind of pattern happening here. It's okay, we'll get used to it. It won't be the end of the world. So now I add one to my number of items. I've added something in, okay? So that's appending, right, at the end. Not too bad here. Now, if I want to, so in terms of performance of this then, right, if we wanted to say, how long is this going to take on average? Does it matter how many items I have on my list? No, nothing depends on the number of items on my list. So even worst case is still O of 1. Average is O of 1, best is O of 1. They're all O of 1. So adding something to the end of a linked list is always constant time, even in your worst case, which is kind of cool. So no matter what, even if I've got a million items, it still adds like that. It'll never have to do any sort of resizing because I don't have an array. I don't need this contiguous block of memory. I just know, okay, wherever the last one was, add a new one somewhere. And when Python says, hey, I want to make a new node, it just says, hey, operating system, give me some space to store this in memory. Your operating system says, here you go, have some space. So what we're essentially tracking, if we were to draw a picture of this here, I should have brought my tablet, I forgot here, sorry. The tablet's so nice. So if we have a node, so typically when we draw nodes, I like drawing them in two spaces here. So we have the data, right? And then we have the next. It's hard to write with the mouse, I'm sorry. Right? So say we had 5 was our first item, and there was nothing in the next. Right? This is just blank for now. Right? So the front of our list, or the first, was this one, right? And then the last was also this one. We only had one item. And we called append. We said, okay, I want to add a 10. We said, okay, well, you no longer have nothing here. Now you're going to point to the next node. We'll make a new node here. Oh goodness, it froze. I'm using Microsoft Word. Why are you freezing? That's so weird. Word's not a very intensive program. So we say we're going to add 10. So 10 has nothing next, but 5's next is now 10. And then we said, okay, well now we need to update last. Last, you don't point here anymore. Last, you now point at the last next. Right? So we've added 10. Does that make sense how we're adding in here? Now, that works out really well for appending. What about, say, getting the front? If we want to get the front item here. You return self.front .data, or no, first, sorry, first. Right, get at the data at first. That was pretty easy. Right, we can get out of here. Sure, the front. What other things might we want to do with a linked list? What if we wanted to get something at a particular index? Right? I think that one is, oh my goodness, what is that one here? It's at, select item, get item. No. This is why I should copy off the book sometimes. We'll come back to that. Maybe we'll say, at, get item at index. We'll come back and put the proper one in here, but later. Now, to get an item at an index, this is where things start to get slow now, because I only know where the front is and I only know where the back is. So if I want to find item number 27, to get to item number 27, I have to go find 27 chains. Hey, first, where's your next? Next, where's your next? Where's the 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 next? Essentially, I have to walk that path because I don't have access to it immediately. So this is going to be slow here. I'll find the right one here once I copy off the book later. So the first thing we probably want to check to say, hey, if my index is greater than or equal to my self.number of items, I can raise an index error, right? Not valid, right? There's nothing at that index. Otherwise, I'm going to say, now to walk that chain of nodes, what we typically do is we have a current node that we're looking at, and then we change the current node. So I'm going to say my current node is self.first, right? Okay, and then I need a current index then. I'm going to start off at 0. And while my current index does not equal the index, right, as long as we're not to the index yet, I'm going to take the current node, I'm going to say the current node, walk to the next one, current node next. And I can take my current index plus 1. Right? And then we keep on going. So if you want the third item, right, I start off at 0 with the first one, go to the next one. Now I'm at index 1. Go to the next one. I'm at index 2. Go to the next one. Now I'm at index 3. So I walk the nodes here from the first to the index. Would that be a little prettier to do it in a range? We could probably do it with a range in a for loop. Right? We could do that. Let's do that. That might be a little prettier. So for, I don't know, node in range index. Because if index is 0, nothing happens. If index is 1, we do it one time. Right? Eventually, when we're done, we can return the current node's data. Right? Yeah.
So when you say in like the third line, if index is greater than self number of items, raise index error. How could that like even happen? Like how could the index end up being larger than the number of items?
So like if you asked for item 27 and we only had 5. So just like when we make a Python list, we do just like, some list 1, 2, and 3, and we said some list of 27. Right? This will fail. I want execute. Oh my goodness. Selection. There it is. Right. You get an index error because there is no 27. That sort of thing. So we're just keeping that from happening with our linked list as well. Yep. I can close that. Right? So we can get individual items out, but we have to find them here. So performance of this then always is going to be, and so a lot of times they say K for index. I don't know why, but really, so it's the index we want, right? So if it's the 27th item, it'll take 27 operations. If it's the millionth item you want, it'll take a million operations. So even though it's K, really, that's, you know, relative in N, we would still say it's O of N. Because the bigger this thing is, the longer this will take. Right? Well, really it's K, but, you know, it still grows linearly with the size of my collection here. So we look at saying how it performs, right? It grows linearly. That's a hard one to say, right? So this one's slow. So getting something out of an array-based list, super fast by index, because we have that contiguous block of memory. But what was slow is adding something at a particular index was slow, or every so often adding something at the end was really slow in a worst case. So performance-wise, we can add really quick all the time, but lookups are going to be really slow. Okay, what about adding something at a particular index, like an insert? I just wanted to say insert some data at an index. Right, like with a list, you can insert at a particular index. Can we do that? Probably do that. So again, we have some weird cases here. Can you insert at 0 if the list is empty? I don't even know if you can do that. I'm trying to remember. So because it becomes the new item at that index, I think it's probably fine to say we could be the number of items. That's probably fine, but you can't be after the number of items. So if I have 10 items and you want to become index 10, well, sure, we'll just add you in. That's really just an append, right? So if that one, and then, hey, if my index is equal to self.number of items, then we'll just call self.append the data. Otherwise, now we've got interesting stuff, right? Okay, this is the easiest way to go about that. Otherwise, now I have to go find what position I'm going to put you in, right? So I think it's probably safe to assume we're not empty either, right? Can we say we can't insert if we're empty? So we, hey, if self.number of items is 0, or first, right? If first is null, first is none. There's a, I don't know, error. What kind of error here? I don't know. Or maybe it'll do an index error too. Doesn't matter too much here. This is just, we're saying we can't insert on an empty list, just to save ourselves a little bit of time. So now what we want to do is we need to find, excuse me, what item we're going to insert this one between. This is where it gets a little bit tricky here. So if I have first and last, here, let's add one more item. Let's add a 15 here, right? Okay. So this one points here. So I have first, I have last, over here. Okay. So if I wanted to insert myself to become the new item 1, right, this one's index 1 currently, right? This is 0, 1, and 2. To become the new item 1, I have to go between 0 and 1, right? To become item 2, I have to go between 1 and 2, right? To go to 3, I just add myself on the end. So to be able to go after something, we have to stop before we get there. So I think probably the easiest one to look at here, we can say, hey, if index is 0, I guess, yeah, maybe another elif index equals 0. So 0 is actually really easy, because if we want to become the new index 0, we just make a new node here, right? Put our data in here, point to first, and then say first you point to me. That one's pretty quick, right? We don't have to do anything else specials. So we can do that. So we can say, let's make a node. So this will be my new node is going to equal a node given the data. Self.node. And remember when we made node, we made it so that we could tell it what comes after it. Usually it's none, but maybe we can tell it what we want here. So we make this node here. The thing that comes after this one will be self.first. right? So it hooks it up so that it's ready to go, already pointing at this next one, right? So we've done this piece. We've made a new node. Its next is first, right? Then after that, we need to say self.first is the new node. Change first, right? Say first, you don't point here anymore. Now you point over here, right? And then again, self.number of items plus 1. All right, if it's not 0 though, if we have to go between something, this gets a little trickier here. So maybe we added a 3. Why not? 3. So now we have index 0, 1, 2, and 3. So if we want to become index 2, right, we're going to go between these two here. So I need to get to 1 before where I want to go, right? So I'm going to go find that current node. So I'll say my current node is self.first. Let's start at the beginning, okay? And then for, I don't know, node in range. Now I don't want to go all the way to the index, right? I don't want to walk all the way to the end there. So if I want to become index 2, I need to stop at 1. So I only want to walk 1 time. So really I want this index -1. Because I don't want to go all the way to the end. I don't want to get to the node that's currently in that position. I want to stop 1 before. Right, so this stops 1 before the desired index. Right? Then I can put myself in between. So if my current node starts at first, and I go to the next one, right? So to go to the next one, right, we'll say our current node equals the current node's next. Just walk to the next one. Walk to the next one, walk to the next one, walk to the next one. Eventually we'll stop at a current node. So if index was 1, it never runs. Right? We range no times, which is good. We stop here because we want to go between these two nodes. If index is 2, we walk 1 time, and now we're ready to go in between those two. So to make the new node then, right, we'll say a new node is going to equal self.node of the data, and what comes next is the current node's next. Right? So I'm going to make a new node here and say, okay, let me throw a new node in here. It's, how about a 6? Its next is this one. Right? Because current node was 5, the 5 node. So 5's next is this one, is 10. So my next will be 10. Right? Then I can say the current node's next equals the new node. Say, okay, hey, current node, don't point here anymore. I come after you. Point to me. And I've put myself in the linked chain, this linked list. Right? We broke that link and put myself in, put the new node in. And now this becomes the new index 2, right? This one is 3, this one is 4. Right? And then again, the self number of items needs to go up by 1, right? Self dot number of items plus equals 1. We've added the node. So the only reason we had to be careful with this one here, because we don't come in between anything if we're the first node. That's all with that one here. So we get a little bit of special handling. It's a little bit annoying here, but we can make it work. Right? So I can insert something at a given index then here. Now how long does this one take? Right? If we think about performance-wise. Is it still k? Right, which is really n. So the more indexes I have, the larger I am, the longer this is going to take. Right? O of k, which is really O of n. We should do that for the other one too. K, which is index. I'm running on a curly braces here. So O of index. They say k all the time. I don't know why it's k. Whatever the index is. So technically it's fast if you want index 0 or index 1 or index 2, right? It's only that many iterations, but because it could be any value of n, right? The average value in n will be half of n, and we get to throw away coefficients, right? So half of n is still n. So inserting is still slow, which is kind of a bummer. Adding to the end, always fast. Inserting anywhere else, kind of slow. So really inserting at the front is constant, inserting at the back is constant. Anywhere else is going to be slow for us. right? What about getting a particular item? Oh no, we already did the get at an index, right? We did that one. We did insert at an index. We did append. Then just add to the end here. We got the front item out. We could even give the last item out if we wanted, whatever ways we want to give access to these things. I don't even know if we need this one right now, but we can come back to it. So this is our basic linked list, right? Oh, we didn't remove. Sorry, we got an item. We never removed. So to remove an item, right? Define remove. Now, there was pop, which pops at a given index, and then there was remove, which removes a given value, right? When we worked with lists, right? So let's do, how about pop? We'll do pop first. So pop takes the index to remove, right? So we have to go find that value. Right? So again, probably make sure we're not empty, or check to make sure that index is valid, right? Make sure it's a valid index. And I feel silly having this code more than once, right? You could probably do something and turn this into a function, right? So we don't have to have the same code twice. Can we do that? So we can say refactor extract method. This is index valid, or check for valid index. I don't know, check for valid index. And it's going to replace that other place too, which is so fun. And then, oh, I got to rename it one more time. Refactor rename, because this should be private. Okay, now we have a private function, check for valid index. That'll raise an exception, raise an error. How fun's that? Right, you don't want the same code twice. You feel bad about yourself. So if it's a valid index, great. Now, if it's the front, we're going to have a little bit of trouble here because that's sort of a special case here. So we can check, hey, if index is equal to 0, right, then we're going to take the front node away. So we're going to have our, I don't know, our data will equal self.first.data. Right, take the data, right, and then self.first equals self.first's next. First is now the thing that comes after first, right? And my self.number of items minus 1. Probably we'll do that every time, right? Probably regardless. So we will take that out of our if here. So we just move first there, and we're done. We're going to return data, right? So first moves to the thing that comes after first. So we've taken it out of the list, right? So if you want to remove the front thing here, you say, okay, first you don't point here anymore. Now you point here, it's out of the list. Right? That was pretty easy, but we have to make sure we move first. Is sort of the problem with this one, right? When we're removing items, we have to make sure our first and last point in the right spot here, okay? Right. Then, if it's not that, right, my other case here, I need to go find the item that we're removing, right? But to remove it here, so before I did this one here, let's put first back here for a second and say if this one's first. If I wanted to remove index 1, which was 5, if I get to the node of 5 and I take it out of the list, the node before it is going to point to something dead, right? I have a broken chain now. There's no links. So I have to stop one before. So same idea, we have to stop one before like we inserted, we have to stop one before to skip it in the list. Because the item before you needs to know what comes next. So we're going to go walk to one before that list here. Right, with my current node in first. So current node starts with the first, and we walk one before the desired index here to get to there. So then to take the piece of data out, so my data will equal the current node's next data. Right? So if I want index 1, I'm going to stop at 0, go to 0's next, grab the piece of data. Now I'm holding on to that. I'll be ready to return that when I'm done. Right? Then I need to take it out of the chain. So how do we take 5 out of the loop? Right? How do we get rid of this one here? We have to change what we're pointing at here, right? We need to say what comes next. So what comes next should be the next, right? Seems a little silly here, but we're going to do that. So we'll say that my current node's next will equal the current node's next. Looks like nonsense, right? But we're jumping over it. We're saying, okay, what comes next is no longer the next node, it's the thing that comes after that next node. Yeah.
So the node that you're skipping over, does that still exist in memory? No.
It'll get garbage collected because nothing is referencing it. So if nothing references it, it goes away. Yep. Yeah, eventually, Python takes care of those details for us. We don't have to care about it. Yeah, there's no manual step. Okay. Later we'll see there's probably something we should do to clean it up. So because it still stores the reference to the data, occasionally weird things can happen where that hangs on, and then this piece of data can't be freed up. We probably don't care too much, but you could go and set your current node's next data to none after that. It's like, sure, the node doesn't store the data. I don't know. I don't generally care to do that, but that's probably a little more proper, right? Because we're going to make sure that this one doesn't reference the data in case this data gets thrown away later, right? The node isn't hanging out there in memory. All right, we jump over it. Now, the problem we're going to have is if we were the last item, right? We know first, we know last. So if I wanted to remove index 4, we'd say, okay, go all the way to index 3, right? Index 3 is fine. Now, grab the data, we got the data, set my next to my next next. Well, my next is none, that's okay, I can be set to none here. I can be a none, but last needs to get updated if I took out the last item. If I didn't take out the last item, stays perfectly fine. But my last sanity check here, right, is going to be if my index is equal to self.number of items minus 1, right? If that was the last item, then my self.last needs to equal the current node. Right? If I took out index 4, that was my last item here, I need to back last up to the current node. Okay, that's the one last check I have to do. So make sure that I don't end up, because if I have last pointing here, but it shouldn't be my last one, it's going to screw up all my appends, right? Because I don't point to this one anymore. So if I start adding stuff onto the end here, I'm now adding stuff off in who knows where, right? I'm going to lose the connections here. So we run into some issues making sure we're keeping everything pointed in the right spot here. So we took care of first, we didn't take care of last. Now, also though, what happened if we only had one item and I wanted to pop that single item off? I left last hanging here as well, right? So we said, hey, first goes to the next thing, which could have been none. That's okay. So before we check that, we can say, okay, if we're removing 0, I can say, hey, if my self.first is equal to the self.last, then my self.last will equal none. Right? If I only had one item, the first and last were the same thing, I'm about to set first to none because first next was none. There was nothing after, right? To make sure last gets set to none. So removing gets to be a little tricky with some of this being this linked list here, because we have to track the first, we have to track the last. Always have to think about those, because we can run into issues here. Right? Take our number of items down by 1, return the data, we're good to go. Okay? So popping something off from a given index then is about how fast? Still O of k, which is really O of n. So still a little slow, which is kind of unfortunate here, right? We said linked lists were going to be really good at adding stuff, but they're not super great all the time. But we can make them better, right? Just like we did with the queues, we start with a bad version, right? Or something that's not quite optimal, and we can do better, right? Does this part make sense before we jump to the next one? Okay, so the piece that we can do to make this faster here is a little bit weird. So we'll talk about it a little bit today. We'll talk about it more on Thursday. It'll take a little time to sink in here. But so far what we've done is we've said, okay, we're a list. You can add, you can append, you can pop, you can insert, all the things like a list does. But so far you looked exactly like a list. So now we're going to add an additional feature to make us special. That'll do more than the list does to give us better performance. And that idea is we are now going to be a positional list. So with a positional list, to interact with the list, you're going to interact with positions. So we're adding on this feature here because if I know this position here, if I say, hey, I'm currently at this position, I should be able to add after that position like that. I don't have to do any walking here because I already have a position. I already know where I am in the list here. So if you know where you are in the list, you can immediately add after it. Nothing has to shift. You say, okay, hey, you now have a next. Now there's a new node over here. So we're going to add this positional class that people will interact with. So it'll be a positional list that people interact with here. And if they keep their position there in memory, so they're going to hold on to your position, you can add immediately. Add super fast stuff here. Now, before we do that, sorry, I jumped ahead a little too fast. Before we do this, it's a little weird if you can only ever add after. Not quite as flexible. So if the positional list only lets you go like down the list, or going this way for you guys, right? And there's no way to go back, it's not going to be quite as flexible. So wouldn't it be nice if we could also go forwards and backwards with this position? That'd be a little bit easier, right? So this sort of list here is known as a singly linked list. There's just single links. So can you imagine what could we do to track the nodes so we could go the other direction? Is there something we could do? So we could go down the list and back the list, or forward down the list, forward the list and back the list? Is there something we could add to our design here? What if we added previous? What if we said, hey, this node comes before me, this node comes before me, this node comes before me, this node comes before me. So if we had double links, we had forward and backwards links. If we're a doubly linked list, right? Then I could, hey, I want to go backwards one, go to the one before me. I want to go next one, go to the one that comes after me. Right? We can add this idea of tracking the previous node as well. So I'm going to leave this all here and not mess with it too much, right? So I'm going to write another class. Okay, is that all right? Now, sometimes it's fun to see the comparisons, but other times it's confusing. I want to keep it so you can reference it too. So a doubly linked list then. My nodes have next and previous. So self.previous, previous is none, is previous, right? So you can tell me what comes after you, you can tell me what comes before you. So I'll make a first, I'll make a last, right? Still number of items is fine, length is still the same. Appending, now, if we're the first item, there's nothing before me, nothing after me. Easy, nothing has to change here. If we're the last item here, right, where we're appending on, nothing comes after me, right? But previous will be self.last. The thing that comes before the new last is the old last, right? So if we go back to this version here, right? We had 5 items, right? We had 3, 5, 6, 10, and 15. If I want to add something to the end here, right? Last is currently at 15. We're going to say, okay, last's next is a new node here. So drop a new node in here. Okay, here's a new node. Let's add maybe 20, right? Its next is none, but its previous is the last. Then, oh, hey, last, your next needs to change. Oh, we didn't change last. Uh-oh, I think we had an issue with that. We forgot to change last. Right, we moved last. No, we did that. I'm sorry. So the last next is the new node. So we updated that, but then we updated last. So I think life is good here with this one, right? So we added in a new node. It comes back to here, and we said, hey, you now point to this one. You have a next, right? So we said the next. We said this one's previous. So we've added it here, and now I can go forwards and backwards with that one for adding to the end. Adding at a particular index here. Again, if we're going to the end, sure, we go to the end. At the beginning here, the next is still the first. We don't have a previous. That's perfectly fine. Previous is still none, right? Now, it might be nice to say this is next, just to be explicit here, that it was the positional argument here, but it's nice to just say, hey, this is the next node here. So to put ourselves in between, now we don't really need to stop at index -1 anymore. And to go in between, we don't need to change anything because our code doesn't need to change now. But so the new node, right? If I want to say, hey, let's become the new index 2, right? So when I put myself here, I'm going to go in between 1 and 2. So the new node's previous will be 1. The new node's next will be 2, right? So the new node's next will be 2. The new node's previous, right, will be the current node. So the next becomes current node's next. The previous becomes the current node. The current node's next is the new node. And the current node's next previous becomes the new node. Right? Oh, actually, before we do that, sorry. Before we do that one, sorry. This is a little silly looking here. Can we change this one? We can change this one. Do you like this or do you want to change it? I think we can change it. Let's change it. Let's say, so the new node's previous next is the new node. And the new node's next previous is the new node. Right? So we drop the new node in between the two. So it knows what it comes before it, it knows what comes after it. And then the new node tells its neighbors, hey, by the way, I'm in between you. The thing that comes before me, I come after you. The thing that comes after me, I come before you. Does that make more sense than going from the current node?
So it's kind of a chain.
Yeah, it's a chain. Yep. So we just drop a new node in here, right? We would say, hey, now I'm going to add, let's put it between 6 and 10. Let's add an 8. So this will become the new index 3 here, right? So we drop it in, and we say, hey, the next thing is this one here. The previous one is this one here. We created the new node. We got to index -1, and we stopped. We made the new node. Now the new node says, hey, thing that comes after me, I'm your new neighbor. Don't point to your old previous. I'm your new previous. Hey, neighbor, the thing that's previous, don't point to the thing that comes after you. I'm the new thing that comes after you. Drops itself in the chain. Right? And then we have 4 and 5. Right? So it takes care of those links for us. Right? So getting is perfectly fine. Now, if you want to be clever, because we can go backwards now, we could, if the index is more than half, we could start at the back and work our way towards the middle. It would save a little bit of time. For our purposes, we don't really care. Maybe we have that as a to-do. Can we do that as a to-do? If index is closer to the end, walk backwards. Right? Again, still, we're never going to get better than like half of n. So the middle now is the slowest point. Anywhere near the front or the end, I can get to quicker, but we're still now half of n. So if we average out half of n across all the n's, right, it's a quarter of n. That's still O of n, right? We throw away the coefficients. So still no better, right? Slight optimization. It's not worth it, but it doesn't change the overall trajectory of this being a linear path, right? The more n I have, the slower this will be. Okay. So to pop something off. Now popping has to change as well, because when we remove something, I was telling the thing that came before me, it's next, right? But now I also need to fix up that one's previous, right? So if we're the first and only one, easy. Should be perfectly fine here. No big worries there. But if we're not, right? Once I set current nodes next to my next, right? Then I need to say current nodes next previous is the current node. It is. It's a little nuts. So
next previous.
yeah. So to take out, so we're saying, okay, jump over me, right? We say this is the jump over the node step. So hey, don't point at me anymore. Point at the thing I point to next.
So next, like I have this one here, instead of being this, we do this.
Yeah. Now the problem with this one is if next is none, there is no previous, right? So we only do this here if we didn't take out the last one. Because if we took out the last one, there's nothing to set a previous on, right? Because it was gone. If we didn't take out the last one, then I know there's a valid node here, right? To point to the previous. So next might be null or might be none if we were the last item. That's the only check here. So to make sure that there is a valid current node next, right? Because if we were that one, there is nothing next. Our next we know was going to be none here, because that was the end of the line. I was the last one. Okay? So now we're a doubly linked list here. So now we track forwards and we track backwards. Now that we're a doubly linked list here, should we do a better version of that before we do the positional? We should do a better version of that before we do positional. Is all this a little bit obnoxious, having to track next and first and last and nones and things like that? It's kind of a headache, right? So it turns out there's a better way to do this one. You know what it involves? Circles, just like our queue. I don't know why it keeps coming back up, but circles are fun. So a circular doubly linked list solves this problem by making sure we always have something that will come next and always have something that comes previous here. So we have a node, right? Knows what's next and first. Now I don't actually need first and last anymore. The circular doubly linked list keeps track of where things are by using a dummy node. Essentially, here's the start and the end, right? It's, I don't know, it's not the head, or it's not the start of it. It's just a null node here. So we'll have self dot, I don't know, I like dummy node. Dummy node sounds funny here. Is a node, self dot node, and it has none for data. It has no next, no previous. But now what we're going to do is we're going to make it point to itself. So self.dummyNode.next is the self.dummy node, and self.dummy node.previous is self.dummy node. What this lets me do is I will never have a none. I will always, if I follow the next, I will always end up at a node. And if I follow the previous, I will always end up at a node. So I'll never have to deal with, hey, what if that one's none here? I have to do something special. So that one's still the same. So now appending, right, is a little bit different. So to add here, and check this out, this is just amazing here. To append, the last thing is always the dummy node's previous. The first thing is always the dummy node's next. So dummy node will point to my first and last, right? Its next will be the first thing, its previous will be the last thing, because this is a big circle here. And because there's always a node, I don't have to do any special handling at all. So I can say self.dummynode.previous, right? That is the current last thing, right? Is going to be a new last thing. So equals a new self.node. Given the data, what comes after this one here? What comes after the last item is the self-dummy node, right? Because the dummy node is always the last thing and the first thing. What comes before that one is whatever dummy node's previous was. Self.dummy node.previous. That's a little long here, but that's okay, we'll get it. Should I bump that one down a little bit more? I can bump it all down. Is that any better? It's a little ugly now. Right? So because we always have nodes, right? So maybe we should put that in here. So where's dummy nodes? Next is always the first item, and dummy node previous is always the last item. That's if we have an item, right? If there are no items, it points to itself because there's nothing here, right? So the next then is the dummy node because we've reached the end of the line, the last items next will be the dummy node, because we reached the full circle here. So our last items next be the dummy node, right? And the previous, what comes before the last, is whatever used to be last. If it was the dummy node, great, here's the dummy node. If it was an actual node, now it's an actual node. My number of items goes up by 1. So inserting at a given index now, we don't need to do any special handling if we're first or last, right? Which is awesome here. So now we just have the else case. And we don't have first anymore, right? So we're going to have the dummy node. So for dummy node, right, that's our current node. We're going to go between the current node and where we want to be, right? So if I want it to be index 0, range doesn't move at all. And I'm going to go in between the current node and the current node's next, right? So my new node goes between the current node's next and the current node. If the current node is the dummy node, that's fine, right? And then my previous next becomes me, my next previous becomes me. We've inserted myself in between. Right? So we just start at the dummy node, and then walking still works the exact same way. We'll always have a node here.
What is a dummy node?
That's it's a node where the next thing is the first, and the previous thing is the last. But that way we always have a node, we will never have nones.
Okay.
Right? So if we were to draw this in a picture here, let me do a new page here. We start with, here's our dummy node. Right? Its data is none, right? That's our data. Its previous is itself. And its next is itself. That's the start of our circular doubly linked list. We have got a dummy node, right? So to add to the end here, we said, okay, let's make a new node here.
So the middle one is always fixed.
Is what?
It's always fixed, isn't it?
Yeah, we're always going to keep this one here. This is for our reference. So that it'll make it a circle. Yeah, this one will always be here to be our circle. So to add something onto the end, we say, okay, the thing that comes after me is the dummy node, right? Because if I'm at the end, I circle back to the dummy node, right? The thing that comes before me is whatever used to come previous, because I'm the new last thing. So what used to be previous was the dummy node. So my previous is now the dummy node, right? So we've added a new item here. Here's 7. With my next and previous. And we say, hey, neighbor, what comes after you is now me. So its next no longer points to itself now. Its next now points to this one. And hey, neighbor before me, I come after you. Right? No, I'm sorry, I did the wrong direction. Neighbor that comes after me, I come before you, was this one here. I come before you. And then neighbor that comes before me, I come after you. So now we're a circle. Right? So now I have a 7. So if I want to append to 10, right? We'll append to 10. We'll make a new node for 10. Right? We'll say, okay, what comes after you is the dummy node's next. Or the dummy node, right? So
I have 2 circles, right?
it'll be one loop. So we're going to put it into the loop here. Yep. We'll see how it fixes up in a loop in a second. So my next will be the dummy node, because the last item's next is always the dummy node. What comes before me is the current dummy node's previous, because the dummy node's previous is always the last item. So what comes before me is this item here, right? Because that was where it was pointing. And they say, okay, hey, thing that comes before me, I come after you. So it no longer points here. This one comes after me. And then, hey, thing that comes before me, right? No, sorry, thing that comes after me, I come before you. So this link breaks here.
What is this whole loop for again?
I'm sorry?
What is all of these for?
So that we can make our code a little simpler.
Is that simpler?
Yes, I promise, it's simpler, yeah.
Are there libraries for that?
Yeah, the linked list is a circular doubly linked list. Yep. Let's see. My arrows are getting a little messy here. Sorry. So we added in the 10, right? And the 10 says, hey, thing that comes before me is next is me. So the thing that came before me, next here then, right, will be me. And hey, thing that comes after me's, before, previous, is now me. So the thing that comes after me, right, my next is this one here. I come before it here. So now its previous is going to be, where'd we go here? This one. I think I lost I already erased the arrow. That's right, I already erased the arrow. So the previous one is this one here. I think the arrow's on the wrong side. Let me put this arrow on the wrong side, on this side here. It'll make it look a little nicer. Okay? So from the dummy node, its next is always the first thing. We appended a 7. That was first. Its next is 7. Right? Dummy node's previous is always the last node. Its previous points to 10. Previous is 10. So that should probably go all the way around. These will look better if I make the arrows better. So this will go all the way around here. Where is this one here? Needs to be to here. There it goes. So previous here then. Right, so 7's next is 10. 10's next is the dummy node. I have too many arrows here. Didn't need those pointer ones. So by having the circle, right, we don't need the special handling. That's really the big gain here. Right? Getting the front item's fine, getting an index is fine, popping an item off. Well, I don't need the special handling anymore. I don't need any of that. If it's a valid index, I'm going to start with the dummy node. We're going to walk till we get in between where we want to grab that item. We're going to grab the item from our next. We can set it to none, and then we need to fix this up here. And I don't need to do any of the special handling either, which is super nice. I'd say, hey, take me out of the list here because I will always have nodes. So my nexts becomes, or the current node, so the thing that comes before me is next, becomes my next. Jump over me. Thing that comes previous to that, right? My next previous needs to become me. So we're going to jump over. So if we wanted to take out an item in the list, let me draw this a little, like, if we just draw it in a circle to start, it looks a whole lot cleaner here, right? So we have a dummy node here with nothing, and we have 3, we have 7, and we have 9, right? 3, 7, and 9. So 3's previous is the dummy node. 3's next is 7. 7's previous is 3. 7's next is 9. 9's previous is 7. 9's next is the dummy node. Dummy node's previous is 9 because that's the last item, and dummy node's next is 3 because that's the first item. Right? So if we wanted to take 7 out of the list, right? This is index 0, index 1, and index 2. If we go to 1 before where we want to stop, right? So we're going to stop here at 0. We can stop here. That might be why it's a little confusing too. Should let's fix that out here. So we don't need to do that anymore. We can go right to the current node's next. Okay? Current node's data, and then set my data to none. Now we can change this here. So we got right to the node we want to remove. Right? We're going to take something out by a given index here. So we'll get right to that node. So we'll get right to node 1, node numbers with the value of 7. Okay? So to take 7 out of the loop, we have to get it jumped. So we say, hey, thing that comes before me, your next is now my next. Thing that comes after me, your previous is now my previous. Right? We're going to break those arrows here. So now we can say current nodes, nexts, previous. So the thing that comes after me, what comes before you, is the current node's previous.
But if I'm here and I'm doing like next, previous, it's the same.
Well, we're changing the value. So 7's next is 9, we're saying, hey, your previous is no longer me, right? Your previous skips me. Your previous is now 3, because that's my previous. So we're skipping ourselves. We're saying my next previous, change the value of that to be the value of my previous, which is the node 3.
My next, go to my previous, did it?
Yeah,
So like 7 is saying 9, go to the one that comes before me.
yeah,
So,
jump over me. I'm no longer before you.
so how did the values change there? So what does 7 become?
7 hasn't changed. We're changing the node here that stores 9. We're saying this node's previous value no longer points at 7, it points at 3. We're jumping it out of the list. And then we do the same thing. We say the previous next is the current node's next. Right? We say, okay, hey 3, you come before me. Your next is no longer me. Change that. Your next is now my next, which is 9.
So now the order is, instead of being 3, 7, 4, it's now 3, 7, 4, 3.
3, sorry, that's a 9. It's a bad 9. So 3, 9. So 7's gone, right? So if you start a dummy node, you get to 3, you get to 9. You get back to the dummy node. 3, 9, dummy node. 3, 9, dummy node. 3, 9, dummy node. Because it's no longer referenced. The 7 is no longer part of the chain anymore. Yep. And then this will go away. So it makes that we don't have to do any special handling if we have the dummy node here. We don't have to deal with managing was first none or was last none, or do we have to make sure first and last have to change here? So it's just a lot easier. We just walk to where it is and replace it. Walk to where it is and replace it. What is this one? Inserting. We can do the same with this one too. So we don't need to, I guess 1 before is fine, because you're going to have to stop 1 before, you're going to have to stop 1 after. Either way will be okay, because we're just putting ourselves in the middle here. Now, what we could do is this code is actually very similar, right, to what we're doing over here. We're setting our new nodes here. So we could turn this into another function if we wanted, right? I guess that's a little bit different. Sorry, removing and adding is a little bit different. We'll come back to that. So now we can insert at a given position. Oh, we don't have first is none, so we don't have any of that. So we said that was going to be if our self.number of items is 0. So if my index is greater than number of items or self.number of items equals 0, that gets to be a weird thing to handle, but really we don't even need to worry about that, because with dummy node not being never none, right, we never have any nones. So when current node is the dummy node, if it's 0, it's great. We don't range. No ranging happen. So current node stays. So the next then is current node's next. Previous is the current node, which is the dummy node. Okay, so this code just works. So it takes out all the special handling, is what's nice about this circular piece here. Right? All right, I got 305. I don't think we've got time for the positional piece. So we're going to talk about positional lists, and then we're talking about how we iterate. How do I make it so I can throw one of these things in a for loop? For item in collection, do something. We can't do that yet.
We're going to have a project on that.
We'll do linked items. So you can build this idea of a linked list. You can write classes that also have that sort of format, if that makes sense for your classes. Rather than having to store the information in a linked list itself, your class says, hey, I know where the next one of my class is. I know where the next one of my class is. I know where the next one of my class is. So it follows these like nexts and previous things without being a linked list itself.
What kind of resource do you think to give for us to study for that?
For this,
Yes.
chapter 7 is all about this. So I'd start with the book, and then if you want more stuff, I can find more stuff for you.
But do you think the textbook is good for that?
So my only issue with the textbook is it does all the inheritance nonsense. So like this becomes this, becomes this, becomes this, or inherits from this. Like, and then if you want to remember what was happening, you have to flip back to see, oh, what did that code look like before? That's my only complaint with it. Other than that, it explains it really nicely. Yep. Yep.
In terms of like YouTube, are there new channels that explain that?
Like some basic data structure sort of things.
Yeah.
Yeah, there's a couple different things out there. I don't know if anyone does it in Python. I'd have to go look and see.
Because usually after the class, I like to watch it again and like,
Yeah.
you know,
Yeah, just go search like linked list data structure. Here's CS Dojo is usually pretty good. They're pretty well selected. All the Udemy sponsored ones irritate me because they're like, hey, go buy our stuff. Go buy our stuff. It's like, don't put it on YouTube then if it's just an ad, but that's okay. Nesso Academy might be okay. That one looks like it's got some good pictures. Linked list data structure in JavaScript. Ooh, that might be a little awkward. HackerRank is probably going to be pretty good for this one, right? That should be a good video. Free Code Camp is great. Linked list for technical interview. A full course here. This would be a good one. So yeah, probably a couple of these should be pretty good. Yeah, if you want more, for sure.
appreciate it.
Yeah, no problem.